Good morning and welcome to today's webinar. We will be talking about ETAP grid, generation optimization for microgrids. My name is Tanuj Khandelwal and I'll be walking through this topic for the next 30 to 35 minutes. We'll talk a little bit about ETAP for those of you who may not be familiar with the program. ETAP is essentially a platform for design analysis as well as operation, control, and automation of power systems. So essentially with ETAP, you can go through the entire life cycle from modeling to analysis into monitoring, operations such as predictive simulation and optimization. The program essentially utilizes a single database with multiple foundations or multiple views, and it's able to utilize offline and real-time analysis information. It includes protection and selectivity modules, and because it's an open platform, it allows for seamless integration with multiple technologies in the system. ETAP basically is broken down into ETAP, ETAP real-time, and ETAP grid. ETAP is the application that you're traditionally used to doing design and analysis. The same platform is utilized by ETAP real-time, which is essentially a model-based power management and automation system. And finally, ETAP grid, which is a combination of ETAP and real-time technologies dedicated to transmission, distribution, and microgrids. So in ETAP grid, when we talk about its components, we're talking about applications for transmission, distribution, and microgrid. And today our focus is going to be specifically only on microgrid. So therefore the product is fairly large and includes full spectrum power system analysis and power management capabilities. Now, before we jump into the capabilities of the program related to generation optimization, let's quickly recap what we mean by microgrids. Different people in the industry have different definitions, obviously, of microgrids, but essentially you can consider a microgrid as any system that can operate when it's connected to the grid and or can operate in an islanded manner. It has its own generation and its own load centers. A single microgrid in the system can exist on the distribution substation, but you can also have customer microgrids which are connected at the feeder level, and you can also have partial microgrids where there are multiple customers joined together to make one larger grid. Then you can essentially have cases within these microgrids where they can actually fracture and become nanogrids. But the basic definition that we'll be using through this presentation is any system that can be operated grid connected or be operated in an islanded fashion. Another example of a microgrid could be a marine microgrid system where you essentially have a ship system with its own power source. The fuel could be diesel, gas, nuclear, as for example in a submarine, with power conditioning to convert from AC to DC or vice versa. And the power conversion, such as the variable speed drives that actually connect into the various loads and the propulsion system of the ship. So here's basically another example of a microgrid type of system. So when we're talking about microgrid design and operations, what we've tried to do is essentially combine the electrical design and analysis software together with the SCADA components or supervisory control and data acquisition components, and as well as a microgrid central controller. So you can essentially imagine the model being designed inside ETAP. The data acquisition is being performed by ETAP as well. And there are real-time applications that run that utilize this model that you've used for design purposes and enrich that model with real-time information for actual control and automation of the system. So the ETAP microgrid controller basically combines the system modeling analysis with real-time data. With the controller, you can predict the outcome of various contingencies, any load changes, any unplanned failures, etc., as well as provide recommendations to the operator on how to take corrective actions. And as you will see later on in the presentation, the recommendations can be things like how and when to start and stop various generators in the system and how to optimally dispatch various sources in the system. If you recall, I previously mentioned multiple foundations. The multiple foundations include obviously a schematic or a single line diagram. Equipment modeling is important because that includes modeling for generators as well as renewable energy such as photovoltaic and wind. So that capability is also included inside ETAP. It's always best to have the protection as part of the schematic, so you have a complete picture from steady state to fault current levels and see how the system is going to operate. Web dashboards or HMIs to make sure that the managers or engineers or anybody who doesn't have access to operations has operations data accessibility without the control. And then obviously there is the unique control logic that is inherent with every single component, such as an energy storage device. When does it charge, discharge, and what are the characteristics it follows? Similarly with a generator, how does the exciter, governor, and power system stabilizer, if there is one in the system, how does that react with the rest of the network? So all of these put together, all these foundations put together essentially give us situational intelligence. It tells us where we are and in what kind of shape we are in. Also, it's important to talk about the control architecture. So when we talk about microgrid central controller, and this is, let's say, at the customer level, and here's my feeder or a distribution network operator feeder coming into my microgrid. I can have energy storage device, photovoltaic, electric vehicles, critical loads such as hospitals, as well as distributed energy resources like wind, fuel cells, and so on and so forth. That could be part of my portfolio or my generation mix. But what's important is we can also utilize ETAP on the SCADA, DMS, OMS side for the DNO or the utility distribution side, and the two systems essentially coordinate with each other based on telemetry going back and forth, as well as certain signals such as generation load and timing. It can also be expanded down the road to things like pricing and market pricing and trading and so on and so forth, and the ancillary services market. But typically the implementation scope includes electrical control and providing reliability for the network. So when we look at the architecture and we break it down further, what we basically see is a SCADA DMS that's sitting at the distribution level. We have a microgrid central controller at the customer level, and then each component, like a microturbine or a PV or flywheel or energy storage, each of them has its own microcontroller. So in the case of generator, it's very straightforward. A microcontroller for a generator includes the governor and exciter. It provides the primary control for the equipment. However, the secondary control or the balancing or the coordination of these individual devices is managed by the microgrid central controller, and it acts as a secondary and tertiary control both. So here again is just a quick representation of the DMS communicating with multiple microgrid controllers and achieving a common objective dispatched by the utility DMS. So in all cases, these components can be ETAP or any other vendor that may exist in the system. So when we are looking at generation optimization, we look at it from a couple of different perspectives. We look at it from a technical perspective, economic, as well as environmental. There's one more perspective, which is operations and maintenance, that fits into perhaps an economic category. Uh, and when we optimize generation, we essentially have to look at power losses, how to minimize those, improve the system reliability, because those are low-hanging fruit, minimize the cost associated with them, as well as the maintenance cost, and then finally, to a certain extent, the greenhouse gas emissions as well, if there are certain constraints associated with it. So when we talk about generation optimization, we're talking about optimizing from all aspects, and it makes it a multi-objective optimization problem. Now, when we are trying to get some value or return on investment from a microgrid, the total cost of ownership in dollars per kilowatt hour, if you are a microgrid developer and you're trying to invest in a system like this, the total cost of ownership can be reduced in three broad categories. There's many others, but these are the three main ones: capital and investment, O&M, operations maintenance, and obviously the fuel cost. And what I've tried to do is highlight some of the applications that the microgrid controller should have that help minimize each of these groups. So when you include a microgrid state estimation, what you're essentially doing is eliminating the amount of hardware that you're putting into the system in order to gain complete system visibility. If you combine power and thermal together, for example, in a gas turbine or a combined cycle, there is a lot of capital and investment that can be recovered right up front because the optimization is happening right at the beginning rather than at the tail end. Same thing with volt-var optimization. By utilizing this, you can minimize the amount of asset upgrades that will go into the system to improve voltage and power factor in the network. However, our focus is sitting down here, which is on the fuel side, and that includes the generation optimization and dispatch. The renewable sources are essentially unpredictable and they don't really contribute to the fuel cost. Hence, we have to essentially optimize all the other sources of the system and balance the network as best as possible with other intermittent sources coming in and out. So when we look at the microgrid application portfolio, there's many applications here. The ones that we'll be looking at are predominantly island detection and frequency control. We'll be looking at economic dispatch and essentially unit commitment. So first of all, when we talk about microgrid state estimation, and I'm just going to pull up a file here for us to take a look at it. In this particular file, what we can see is a microgrid system. There are about 6 different sources. There's no utility connection. Hence, this is a permanently islanded microgrid. And the microgrid is actually getting real-time information from the network, things like voltage, real reactive power, frequency, and so on. And this information is being updated on a per second basis. There may be a little bit of a lag on your side, depending upon the connection speed that you have. I'm going to go ahead and change the colors to something that's a little bit more easier to read instead of a black background for those of you who may be projecting this on your corporate network. So here we can see in blue again is my meter measurement, and in this reddish brown color I can see my state estimator output. And what we notice here is I have a flow shown on my 13.8 kV bus, and there's a flow shown on the 2 breakers that leave this particular cable in the system. So I have about 3.2 megawatts and about another megawatt here circulating through this bus bar section. And this circulation is actually being shown via state estimation. So utilizing the measurement that I have upstream on the generator, utilizing the model that I have previously built and used for various calculations like power flow and short circuit and so on. I'm using the same model to figure out what are the estimated flows throughout the system. If I know the estimated flows throughout the system, I can therefore have a little bit of a better optimization where to place additional metering points in the system and minimize some level of hardware where it's really not necessary or essential to the operation of the system. So that's as far as the state estimation is concerned. Those are the results we are seeing on the one-line diagram. One of the benefits that we get out of the state estimation is the ability to perform a model validation. And what I mean by model validation is the ability to compare the real-time measurements, which are shown in this bluish color, and comparing those with the estimated values for the same location. So it happens to all of us who are involved in power system analysis. Whenever we are working with an electrical model, the model is only as good as the quality of data plugged into the network. And what this tabular view shows us at every instance in time is where is the meter value that's coming from the actual system, and what is the estimated value based on my electrical model. And the deviation tells me how close or far away is my model from the real life operation of the system. So we are basically comparing the as found system real time with the as found system estimated or modeled. And the fewer or the smaller the magnitude of deviation in my table here implies I have a higher quality model. For example, the reason you may have deviations between the two is if you pull the cable, which is 500 feet in, and that's what's written in an AutoCAD file. And if you actually pull that cable in the real system, it may not be 500 feet. 500 feet was estimated at the time the system was designed. Reality may be 550 feet, it may be 450 feet, it may be different. And every single minor change in impedance adds or compounds to the delta offset or the deviation from the actual network. So this tool, which is called a comparison table, is particularly beneficial to identify where the problem areas might be in the system. So jumping back to where I was, that's essentially a byproduct. Coming back to actual generation optimization. So here what we are essentially doing is multiple items, as I mentioned earlier. We are combining load frequency control, and that's the capability where the program is actually looking at system frequency. It's looking at actual generation and the interchange, if there is one, or the power exchange between your microgrid and the utility system. And it's looking at the scheduled frequency. And depending upon whether you are connected to the grid or not, the program chooses between different objectives. If I am grid connected, I will not be regulating the system frequency. Therefore, the scheduled frequency is no longer relevant. I will be more interested in the interchange, how much power I'm buying or selling based on my agreement or my tariff with the utility. A lot of industrial plants which can operate as microgrids tend to operate with net zero power, which implies that the interchange values or the power flows are maintained close to 0 megawatt. The utility is there for reliability purposes. So the frequency control allows us to control the network when we are grid connected, and it automatically detects when the system has been islanded from the network, and then start regulating the internal frequency of the isolated system. The economic dispatch essentially looks at the conventional generation fuel cost and economic constraints, and it looks at the energy cost curves from the power grid. Therefore, it implies it's essentially looking at the tariff or the rate at which you're buying and selling power and the rate at which you're burning fuel to generate energy. And then it essentially decides which is the most optimal generation source and which source is closest to the load such that the losses are also minimized. So again, it's a multi-objective solution. And then finally, we have unit commitment, which actually looks at the operations and maintenance side of the generator. Again, for example, if you have diesels in the system, these have a lot of moving parts and they require a higher degree of maintenance than a conventional gas turbine. So we have to look at the generator runtime, the maintenance limits, and the spinning reserve that's available, and decide when to start and stop generators in the system. So when we combine all of these four technologies, the frequency control, power exchange control, economics, and the ability to start and stop generators in the system, we come up with a final regulation or a dispatch in the system. And that essentially is given to the operator to make sure that he knows this is the most optimal solution for my network. The operator then has a choice to either allow the program to automatically control the system. So ETAP can actually send the dispatch directly to the generators, or it can act in an advisory mode. And we'll see the capability viewer where you can see where the switch can be made between supervisory and advisory control. Now, as far as frequency control is concerned, there are multiple objectives. Not to go into the details of each one of them. Each of them serves a purpose, but the one that we utilize majority of the time is the auto switch. And what that means is we automatically detect if there's an island formed in the system, because inside ETAP, unlike conventional SCADA systems or hardware-based systems, we know the model connectivity, and as we get the status of various devices in the system, we can easily decide based on connectivity which part of the system is islanded and which one is grid connected. And if it has fractured into multiple pieces or subsystems, we can essentially detect that and create a strategy for control in each subsystem. And these are essentially the control modes, which again, each of them serves its own purpose, and I will cover those shortly. So as far as the program is concerned, I will jump straight to the mode in which I'm actually running my optimization. And before I actually start the optimization process, I can actually define a control case or scenario. I can have multiple scenarios. So therefore, what it allows me to do is set up different strategies for different ways of operating the system. That means if you have a different control strategy in summer versus winter, or if you have a different strategy at day during or during night, or under various unique operating conditions of the system, these can be pre-created by the engineer and made available to the operator with an easy to recognize name, so that the operator can easily switch between the control strategies without having to reconfigure the system. So for those of you who've used ETAP before will recognize the concept of a study case, and it allows for maximum flexible control over how the program is solving various optimization objectives. So here we are actually looking at the study case. We have different calculation cycle times. So as I mentioned earlier, the frequency control, economic dispatch, power sharing between generators, as well as the ability to start and stop. Each of them can be run on its own calculation cycle, though they all interact with each other and generate a consolidated and agreed upon dispatch value that doesn't conflict uh, between one another. So we have unique ways of making sure that uh, participation or the combination of results is happening in a coordinated manner. The rest of these options are related to optimization, so I can essentially skip those. The most important one is the objective page, where we essentially define our objectives for frequency control, whether the power sharing is enabled or not, our objectives for starting and stopping generators. As you can see, is based on fuel cost and running hours, including maintenance considerations. And then finally, economic dispatch or optimization objectives, which is based on, again, multiple objectives such as fuel cost and real power loss and so on. In frequency control, we basically specify our control area. This application can also be adapted for transmission energy management systems, where you can have multiple areas or control areas, in which case this list would be much longer. But since we're dealing with a single microgrid, we only have one control area to deal with. And then we have different generators, obviously, in the system that I'm utilizing in addition to any of the renewable sources. Only the conventional generators are shown here because they are the only ones that are easily controllable. Even though you can technically apply some sort of control to the inverters and manage some level of voltage control from the renewable sources, the focus of the generation control here is megawatt, and then the secondary objective is reactive power or voltage. So you can also set up the voltage regulator and the power factor controller here. And then finally, you can specify the constraints such as voltage and branch flow constraints in the system. So that essentially is a quick summary of the types of variables or the parameters that go behind setting up a generation optimization case. Now, once the case actually has been set up, then the next step for us is to essentially run the calculation, and then we can quickly launch our generation optimization viewer. And that's essentially the primary interface that the operator would be looking at in order to understand what's going on with my electrical system. So the viewer is set up based on various control areas, and here, as you can see, I have subsystem 1, 2, 3, and 4 represented as S1, S2, S3, and S4. So therefore, the program is automatically detecting that even though I have one common area, but that area actually has been fractured into multiple regions. So we are essentially tracking each region independently. Now, within these regions, we can see that these generators are actually offline, and therefore they belong into a completely different area. And we can see here I have 3 different generators that are actually in manual control. So the operator essentially has full flexibility on what he wants to do with these units. But our activity or the main work that the program is doing is actually happening down here between these 3 generators. So here we can see they are in full control, which means I'm applying frequency control, unit commitment objectives, economic dispatch. All the objectives have been applied at the same time. I can see my economic dispatch results in my last 3 columns here. I can see my frequency control results in this column here called ACE or control error. I can see my operating values which is basically the values that the program is measuring from the system. And then finally, I can see the target values that the program is suggesting based on different objectives in the network. Now, I'm operating in a open loop environment, so any control signal that I apply will not really have any effect because there is no generator to which I'm connected to in reality. So we are essentially operating mostly in advisory mode. And what that implies is the program is essentially giving me the recommendations. And at this point, it's my choice whether I would like to dispatch these target values or these settings to the system. Now, what's interesting here is the capability or the result that's coming from UC, or essentially unit commitment. And it's essentially telling me to stop one of the generators and actually let the other two keep running. So in order to understand that, the program also has to keep track of spinning reserve. And the spinning reserve is a combination of actual spinning reserve detected by the metering devices in the system, as well as the forecasted values from the renewable sources. So in order for me to determine the spinning reserve, I have to look ahead, include that capability in along with the current load in the system, and then decide, do I have enough spinning reserve in the system to keep operating the system safely or not? And that minimum spinning reserve, again, can be defined inside the control strategy, inside the study case. And the program will make sure that there's a certain minimum spinning reserve maintained at any given point in time. And if it feels that you're going to fall below that minimum spinning reserve, then essentially it will give the command to start another generator if it is available in the system. So by controlling when you start and stop the generators, you can have some measure of fuel cost savings, especially in microgrid scenarios in remote locations where it's very expensive to bring fuel, such as islands or forward military bases and transportation, such as marine systems. Fuel is always a precious commodity, so that essentially can get higher priority, and that can be actually defined inside the control objectives. Now, just for the sake of demonstration, if I was to go to one of these generators that I have in my system, and we can essentially pick, let's say, NDG2. So if I go to the properties for this generator, I can see what the fuel cost curve looks like. I'm using an equation, a polynomial equation, to define the cost curve for this generator. And just for the sake of demonstration, I'll increase the fuel cost of this generator. So that's NDG2. It's currently running. The program's telling me I need to stop NDG1. So I've actually changed the fuel cost that's seen by that generator, and that could actually happen in real life where you're actually switching between different fuels. And the next cycle, when the program is checking to see which is my cheapest generator, you can see that it actually flipped. It's actually now telling me that I should stop NDG2 and actually start NDG1, because it's actually cheaper to run that. And in this particular example, all three of them are the same size, just to make sure that it doesn't get too complicated when we look at it from a demonstration perspective. So all three of them are the same size, but now one of them is more expensive. So as expected, the program is flipping and choosing a preferred source in the system. So that essentially gives us a broad summary of what is essentially happening in the optimization side within the program. Now, within each area, you have the capability to double click on any of these areas in the system and actually change the control strategy of the area itself. So right now I've set this area to frequency control, which means I don't really care about the tie line flows in the system, because in this network there aren't any. All I care about is just the frequency, so hence I set it in that mode. But if I was in a situation where the system can operate grid connected and operate islanded, I would set it to auto switch mode and implement it, and then let the program decide based on the topology of the system which is the best control objective for me. So whether I should be operating in droop mode with my conventional sources, or should I switch them to isochronous mode and actually start regulating the frequency. In addition to that, there's many other minor capabilities inside the program. You're actually able to export this information out into Excel. So if you're actually trying to gain confidence in the system, you can actually run various tests with the generation optimization routines, generate the output and export them to Excel for further analysis. So we do have that capability. If you were a transmission system, we actually even have the ability to do time error correction. However, in case of microgrids, that's really not important. However, for transmission networks, we can definitely include that. So as far as frequency control and economic dispatch is concerned, that's straightforward. One's dealing with frequency. The second one is dealing with cost and losses in the system. And then when we deal with unit commitment for microgrids, we're actually dealing with starting and stopping generators based on these objectives. The unit commitment in a traditional sense in a utility is quite different, because that actually relies on day ahead forecast. This unit commitment actually relies on a much shorter term, a shorter horizon forecast. So we are able to actually run this on a few second to few minute basis, because in case of renewable energy, the wind and solar output can dramatically change in a matter of seconds to minutes, depending on the situation. So we have to be able to do a quick look ahead constantly and keep providing that input into the unit commitment program and decide when to start and stop generators. So we can essentially bring in information from the actual engine, when it was last started, how many hours it has run since the last start, its maintenance counters, its lifetime counters, as well as the alerts. So we can also send out alerts to the operator to let him know when the unit is approaching its maintenance milestone, so that he doesn't run into a situation where he has to shut down the unit for maintenance and jeopardize the reliability and security of the system. Now, when it comes to the microgrid control, obviously control requires many different types of modeling capabilities. So we also utilize our current technology, which is UDM, or user-defined dynamic model, to essentially create dynamic transfer functions for various components. In case of generator, that includes governor and exciter. In case of inverter, it actually includes the inverter transfer function. When it comes to energy storage and fuel cell, that's a little bit dependent upon the manufacturer, because these models tend to be proprietary. So those are essentially handled on a case-by-case basis. However, the program actually has a Simulink type interface, similar look and feel, but it's actually integrated with ETAP, so it actually works through the dynamics using the input and output for various components. So when we actually deal with generation optimization, we also have a supervisory controller similar to this that you can specify the proportionality gains and the time constants and adjust or tune this transfer function to behave in a smoother manner. And what I mean by that is for any small change in the system, there shouldn't be any drastic corresponding balancing change. It must be gradual. So some level of tuning obviously must be done, and this is actually done inside the study case again, where the control strategy is defined. So over the course of the last 2-3 years, we've actually deployed about 20 different microgrid systems. Some of them include renewable energy sources, and some of them are purely microgrid from a standard definition perspective. But they all require generation optimization. They all require load balancing or load shedding. And we have been essentially including those in these systems for quite some time. And we have a number of case studies that are also available for those of you who may be interested in any specific type of microgrid. So in conclusion, what I would like to say is you can utilize ETAP to model a microgrid system. So that includes all the components that go into a microgrid design. Obviously perform various calculations like power flows, short circuits, coordinations, and so on. Connect the real-time data to the electrical system and start monitoring the operating state of the network. Somewhere beyond that is the ability to predict and determine the what-if actions. So what if the operator was to close this breaker? What will be the impact in the system? We can also control or send control signals from ETAP automatically or manually. We include optimization routines like generation optimization, voltage optimization that we didn't really talk about. But there's various optimization routines that are part of the program that operate in real time. And then that completes the life cycle. So if there's any change or expansion in the system, what we always suggest and recommend is that the model that is the single source of truth, the base model that's used for the real-time system, is the one that gets updated first. Those new changes are analyzed, and once they are implemented, you can actually utilize the concept of data revisioning inside ETAP to merge those changes back into your as-found model, add the incremental devices that you want to monitor, and then continue on with the life cycle of the system. So since we are out of time, this webinar essentially lasted about 45 minutes. At this point, if you have any questions, you can essentially ask those in the questions panel. We'll be online for the next 15 minutes to answer any questions you have. If you don't get a chance to ask the questions or you have to run to another meeting, more than welcome to email us. My contact information is given. You can also email us at sales@etap.com. And we'll be more than happy to get back to you or arrange for more detailed discussion related to generation optimization in a microgrid or in a utility environment. So once again, thank you very much for attending, and please keep a lookout for email announcements regarding the next webinar, which will be focused on some of the new capabilities in ETAP 14. Thank you very much.